Wow, nice crystals.
Thanks. I'm recrystallizing a bunch from my lab this afternoon. You know, it really feels good to turn a mess into something beautiful like this.
Oh yeah. Recrystallization is a basic purification technique. Let's watch how the stagehands do it.
Purification of a solid by recrystallization depends upon the fact that different substances have different solubilities in a particular solvent. Generally, the impurities make up a small part of the mixture and remain in the solution. An impure solid can have other compounds adsorbed on the surface, on the edges, or occluded, which means trapped in the crystal lattice. Dissolving an impure solid in a suitable solvent creates a disordered array of the desired molecules and impurities in solution. As the solution slowly cools to room temperature, crystals form as the molecules fall into a definite pattern. Only the same type of molecules easily enter the crystal lattice, and the crystal grows along its outside surface, leaving the impurities in the solution. The first step in a recrystallization is selecting a suitable solvent. In an ideal solvent, the solid is virtually insoluble at room temperature, but very soluble when the solvent is heated to its boiling point. To find a suitable recrystallization solvent, test the solubility of your compound in different solvents. Ethyl acetate, methanol, hexane, and water are solvents frequently used for recrystallization. You will need the solvents, test tubes and a rack, a test tube clamp, pipettes and bulb, a spatula, your compound, and a beaker of water on a hot plate. Place a small amount of solid in a test tube. Add about 1 milliliter of test solvent. If the solid dissolves immediately at room temperature, the solvent is not good for recrystallization. Repeat with another test solvent. Place a small amount of solid in a clean test tube, then add about 1 milliliter of the different test solvent. If the solid does not dissolve, place the test tube in a hot water bath with a temperature at the boiling point of the test solvent. If the solid remains, then this solvent also is not suitable. Repeat this process once more with another solvent. If the solid remains at room temperature but dissolves in the hot solvent, then finally this solvent is a suitable recrystallization solvent. The first step is to find a suitable solvent. Remember, the solid is insoluble in cold but soluble in hot solvent. In the second step of this technique, you dissolve the solid sample in the suitable solvent. You will need an Erlenmeyer flask for the solvent and another to hold the crystals, a hot plate, some boiling stones, a dispo pipette and bulb, and finger cots. Add 2 boiling stones to each flask. This is important because boiling stones contain air-filled pores which serve as sites for bubble formation. Bubble formation prevents a heated solvent or solution from bumping and leads to smooth boiling. Heat the solvent, and once it's at its boiling point, remove it from the heat. Add enough hot solvent to obtain a loose slurry. Swirl the flask to dissolve the solid and place this Erlenmeyer flask on the hot plate. After 10 to 15 seconds, add more solvent dropwise, continually swirling pausing, adding more solvent, swirling, pausing, and heating until all of the solid has dissolved. When dissolving the solid, our goal is to obtain a saturated solution. Now that the solid is dissolved, you must make a decision. Do you expect a colorless product, but your solution is highly colored? If so, you need to add a small portion of decolorizing charcoal and do a hot filtration. Does it contain a few insoluble particles other than boiling stones? If so, the next step is a hot filtration. Recall that for a hot filtration to be effective, everything you use must be hot to prevent crystallization in the filter funnel. Use a heated, short-stemmed funnel containing a fluted filter paper sitting in a heated Erlenmeyer flask. This flask should contain a few milliliters of recrystallization solvent. The solvent vapors will wet the filter paper and keep it in place. Pour the hot solution slowly and steadily into the center of the filter cone. If crystals should form in the filter paper, use fresh, hot recrystallization solvent to dissolve the crystals. Later, the filtered solution would probably need to be concentrated. Now you are ready to cool the solution, causing the compound to crystallize and leave soluble impurities in the solvent. Remove the flask from the heat and place it on the bench. Leave it undisturbed until the temperature of the solution approaches room temperature, and crystals begin to appear in the flask. The size of crystals that form varies with the rate of cooling. Rapid cooling tends to form very small crystals and may also precipitate the impurities out of the solution along with the small crystals. During cooling, it is very important that some crystals have begun to form before putting the solution into the ice bath. The Nobel laureate, the late Professor Robert Burns Woodward, in his essay Organic Compounds, Retrospect and Prospect, stated that crystallization is one of the most beautiful processes known, and no true chemist fails to experience a thrill when he brings a new form of matter into the crystalline state for the first time. Often, this is a very difficult process requiring great practical skill and persistence. In this and other practical respects, organic chemistry is a craft, and the more craftsmanlike the approach to it, the more it is likely to be successful, and like all things made with care and affection, beautiful. Wait until the majority of crystals have formed at room temperature. Then place the flask in an ice water bath. It looks so easy, but what do you do if no crystals form? When the flask is on the bench, or even after longer cooling in an ice water bath? In this situation, you must induce crystallization by nucleation. Scratch the inside surface of the flask at the meniscus with a glass rod to provide small pieces of glass around which the crystals can grow. Another method is to seed the solution with a crystal of pure compound if one is available. If neither of these methods work, the solution should be concentrated further. Now that the crystals have formed, they need to be collected and dried in order to determine the yield from the crystallization and to analyze the purity. The separation of crystals from the supernatant liquid is best achieved by vacuum filtration, which has the added advantage of drying the crystals. In the apparatus shown here, vacuum is applied to the filter flask through a water trap. Place the Buchner funnel on the filter vac adapter in the neck of the filter flask and then add filter paper. Moisten the filter paper with a little of the recrystallization solvent. Close the stopcock on the water trap. Remember to wipe the crystallization flask free of water. Swirl and pour the crystals and solution onto the center of the paper. Add cold solvent and swirl the crystals remaining in the flask into the funnel. When the liquid is all sucked through, release the vacuum by opening the stopcock. Wash the crystals with a little cold, clean solvent. And reapply gentle suction so that the fresh solvent passes through the crystals but a little slower. Finally, apply full suction for a few minutes to dry the crystals as thoroughly as possible. Release the vacuum at the stopcock. Remove the Buchner funnel and use a spatula to transfer the crystals to a watch glass. In this step, any boiling stones which remain from the crystallization procedure may be physically separated from the crystals. Once the crystals have air dried, the product is ready for characterization.
This recrystallization worked well. Let us again review the steps in the recrystallization process.